Hello, I'm Vlad and I'm glad to present problem number 3 from Prepared Problem Set 2022. That's about cyanotype, Prussian blue and related compounds. This is a kind of problem with very simple answers and a huge amount of text. So the reading skills are quite important here. It begins with the introduction of different kinds of Prussian known Prussian blue compounds like this Tern blue, Prussian green, Berlin green, and Prussian brown, and William white, all those historical names. And then you are asked to write the equations like this. That is pretty easy because in the first one you can see that nothing happens, so you just need to multiply the ionic charges, and that means you need to put 4 cations in order to balance the total charge of -4 in a complex like this. And you also need to put 3 anions. So overall you get ferrum 4, ferrum 3, Cn, now it's 6, and then you multiply by 3. That's it. Of course you can rewrite it as iron, and now 8 plus 4, that is 13, Cn 18. Nice formula, isn't it? And the same you can do for the rest. This way you can get that is A and B should be ferrum 3, ferrum, Cn 6 twice, and for compound C it is beautifully ferrum, ferrum, Cn 6, and that's it. And the last one is similar to the previous one, but we just change some oxidation state for iron and we get 2 potassium inside the structure. So that is potassium 2, ferrum, ferrum, Cn 6. As simple as that. We can go to the structural point where you're given the formula for another compound. Of course, it is another, so we don't duplicate the questions. That's how authors usually would like to put the problem together, that you see there are 4 examples of similar compounds with quite similar formula, and you are giving the 5th example right here with potassium, iron, iron, Cn6, and then the bracket here. And for that structure, you are given the formula. Now let's just spend some time on analyzing this formula. You can see that you have iron 3+, which are situated at the edges and also in the middle. And therefore, let's just calculate how many atoms do we have. If it's in the middle of the cell, then it counts as just 1 atom. And then you have also 12 edges for the cube. And each of them is divided by 4 other unit cells. And therefore we just multiply by 1/4. Overall we have 4 atoms of iron 3+. Now let's do the same for iron 2+, which are at the corners and also at the faces. There are 8 corners, multiply by 1/8, and you have 6 faces which are shared with between 2 unit cells. So we multiply by 1/2, and we have 4, which is great. So that is right. And then you have potassium plus, and for that we have, you see, those green, no, that is orange. All right, so that's orange ball within the subunit of the whole cubic cell. And you can definitely mark that there are 4 of them, and they are not shared with any other unit cells, and therefore we'll have 8 potassium atoms. How about Cn group? Well, that is a bit more complex, but we can do that as well. So you can see that they are at these edges of the proper unit cell and also at the edges of sub-unit cell. What we can do? So just let's speed up. Let's take only one sub-cubic cell like this, and we now can see that there are 12 edges, and each is shared with 4 more subunit cells. That gives us 12 multiplied by 1/4, and then we should account that in the whole unit cell you have 8 subunit cells like this, so let's multiply by 8, and overall we get 24. So if we now derive the formula, it is potassium, iron. Yeah, something is odd here. Let me check. Maybe I have miscalculated something, because now it seems that the formula is potassium 2, iron. Oh, yeah, we can just write the numbers that we've got. Potassium 8, then ferrum 2, ferrum 4, Cn. We divide it by 6, and we put here. Wait, what I'm doing? I don't need to divide, so it's just 4, and I put here 24. And now we can divide everything by 4, and we have the formula which reads as potassium 2, ferrum 1, then another ferrum, and then Cn6. That's it. But it doesn't correspond to that formula given here. That is puzzling me. So is it something wrong with the derivation? That you can check. Of course. No, please, Artemi and Mikkel and others who are following the video, you can correct me. Of course, it's not 8. We have 4 atoms, and you can clearly see that. Nice. If you do similar mistakes as I do during the IChO, you must allocate about half an hour after the competition, well, before the deadline, and check all your answers for that kind of silly mistakes. All right? So that is 4, not 8. It would be 8 if all the cubic holes are filled with potassiums, like this one, that one, here and there. But we have only 1/2 of all cubic holes filled, so it's just potassium, and then ferrum, Cn6. Whew. Now the next question, 3.2, is the one why we would like to go into the D level splitting, and that is about drawing electron configuration of high spin ferrum 3 and low spin ferrum 2. And that is an amazingly simple question, because in the octahedral ligand field, the splitting diagram looks like this. So instead of 5d orbital levels of the same energy, we will have 3 and 2 splitted. That is called splitting parameter delta O. And for iron, 3 plus. You just now start to calculate. In general, iron has 8 electrons, and you subtract 3, so you have 5 electrons left. What does high spin mean here is that when you fill in the electrons, they must be of the same direction, like this. So that is very simple, and you can see that those all levels are half-filled, and these are also half-filled. That is good. The same we can do for iron 2 plus. The same type of diagram, because it is octahedral ligand field, just octahedral environment. And for this one we have 8 minus 2, so in total we have 6 electrons, and it is stated that it should be low spin. Low spin, that means that we pair them together, and overall we get the completely filled energy sublevel. That is the basics. Beautiful, beautiful, simple question. And we can go further. Now we are asked about on the previous slide we had this unit cell like this, which is a beautiful one, and that corresponds to this formula. However, the Prussian blue, if I'm not mistaken, is it Prussian blue? So this Prussian blue has a formula which is A, and we solved it before, so the formula is ferrum for ferrum Cn 6 3 times. And now we're comparing to unit cell, which is ferrum Cn6 4. And you can see that the difference between them is just this subunit, ferrum Cn6. So what does it mean? We are asked about Prussian blue with a chemical formula exactly the same as A, also takes a similar cubic structure but with defects in the framework. Determine the number of atoms, specify the type or group cyanide in each unit cell and indicate the type of defects. Alright, so the defect is usually just vacancy. So you have unit cell. In unit cell you have sites which you usually occupy. Sites are lattice nodes, and if we have something in between those sites, this is sometimes called holes, and we sometimes occupy the holes. Like in this structure, potassium is put into the cubic hole in between all these filled sites. And now out of that structure we just need to subtract this unit. So instead of filling some sites, we create vacancy at that site. And we can clearly see that we are creating a vacancy at the site where the oxidation state is equal to now let me check. So that is 3, so that is 4 minus, and that is 3 plus here, and for the oxidation state is 2 here, right? So we are taking the iron with oxidation state of 2, and then we are subtracting also 6 cyanides. So how should it look like? Let's say that we are let's think. May I draw with some other color? Sure. All right. So we just delete this, and we delete those here, and we delete this group here, delete that group here, delete that, and delete that. So that's it. We just created a vacancy, which is some huge octahedral hole in the structure. And so it's not bad at all. Overall, that structure is still stable. So it's kind of also beautiful. So you just create a bunch of vacancies within your structure. Let it look like this. You have still a very stable symmetrical structure. Now that we have just answered that question, we don't need to draw, but we have to identify that this is octahedral hole vacancy, and then cyano groups are taken from edge, and in total how many we have? Just one vacancy for ferrum 2 plus, and we have 6 vacancies of Cn at the edges. That is it. Now you have again a very long text to read. I'm going to skip that question 3.4. That's just equation. Again, I'm repeating that idea that you can skip some questions also during the Olympiad. It doesn't. You just take your time. You plan how you solve, and if you think that some questions requires a lot of reading, a lot of calculations, or a lot of thinking, and you actually would like to switch to something more easy for you, then do that. And on the title sheet, you just mark that I have skipped 3.4 maybe I would like to come back to that, but maybe I just leave it as it is. And now we are going to point 3.5.1, and that's about dark red cobalt PBA precipitate is prepared by mixing potassium aqueous solution of ferrocyanide with cobalt chloride. So that's a bit tricky question, because if you just put them together, again, you're just putting cobalt 2 plus, I think I have now red, which is good, and you're putting ferrum CN6, and now we can calculate that as 3 minus. It's easy to note that you require, what do you need? Let me think. We have also potassium, I forgot, of course. Yeah. So we get the structure, and there are some other hints in the text that is the correct answer. So easy. However, it is actually not so easy, because there might be, it doesn't, we don't know it yet, but we can exchange the atoms. So the right formula could be like this, so that the oxidation state for iron is not 2 but 3. Anyway, the formula is the same. So if you just write it as um, like that, then it is absolutely correct. You will get all the points. But then the next question implies that there is something might be happening, because you are giving possibilities. Like now we are checking the magnetic properties of that complex, and it has a very weak paramagnetism at low temperature, but its magnetism is significantly enhanced under the red line irradiation. Oh, that's it. So the red line, we're actually changing something here. So identify which of the following statements provides information related to the magnetic phenomena of G. And now we have to decide. In the as prepared G, the oxidation number of cobalt and iron are 2 plus and 3 plus. That is actually A type, right? And then the same statement, but cobalt and iron has oxidation state of 3 and 2 plus. And that is B statement, because you see we have different oxidation states. So we need to decide which one is the correct one. Let's go to the next one. Under radiation, the transition from iron 2 to iron 3 occurs. That is C. Under radiation, the transition from iron 3 to iron 2 occurs. That is D. Under radiation, the transition of electron from T to G to E to G of the metal cation occurs. Actually, we just skip that, because in the text before it was given that the Prussian blue color is due to the transition between oxidation states, and that is given here. And what I'm again stressing, that while you are reading the text, you should highlight something for yourself, so that in the next questions, if you have something related to that text, you can just go back and see exactly what you need to solve the question. Whew. So let's go and see where was it. There's a whole this thing is not important at all. The next one, for instance, the names, the typical method for the preparation, yes, and then often involved formation of blue material called Prussian blue. Yeah, where was it? It's not here. Maybe I have misread it right now, but it must be somewhere here. Not right. So the blue color is due to the change transfer between. So that's it. So your question is about the color. Your answer is hidden here in the text at the very beginning. So if from the very beginning you just highlight for yourself, then later you will remember, oh, there was some mentioning about that, and that is definitely not the case here. So it's not about some transition from T to G to E to G. It's about the transition between oxidation states. And therefore we go to point F. In the above cases, these two kinds of cations, cobalt and iron, are all in low spin state. Oh, that is something that actually we should check. Um, so let us now compare something. Let's draw those diagrams like this for iron 3 plus and iron 2 plus. And the question is about low spin states or high spin states. Let me just change it. So let's put 3 plus here on top and 2 plus below, so that together this is the formula with cobalt 3 plus, and these two together form the formula with 2 plus for cobalt. And now for iron 2 plus we have 5 electrons, and therefore its most stable configuration will be like this. No, sorry. Now I have miscalculated. The most stable for that will be like this, so it has 6d electrons. This guy has 5d electrons, and it will be better to put them all on different energy levels. Now with cobalt 3 plus, how many electrons do we have? Cobalt has in total 9 electrons, minus 3, 6. So it would be much better to put that like this. And cobalt 2 plus has 7 electrons. Oh, how should we put that? Well, there is no good option for that. But in the question we have, yeah, let's put now all into high spin. And you can see that now we have 7, and it's still not a good option for cobalt 2 plus because one orbital is not filled. It's a kind of asymmetrical. But this combination is great. You can see that both iron 2 plus is completely stabilized by filling all the sublevels, and then cobalt 3 plus is also stabilized by having the same configuration essentially. And by doing that analysis, we can conclude, now this might be the case that we have low spin state which corresponds to F case, and this high spin state should correspond to G, but the high spin state is not really stable for cobalt 2 plus. Actually, even if we put that into the low spin state, it would be also not so good because you will have 1 electron on top here. And let's read the last one. In the as prepared G, these two kinds of cations are all in low spin states, but under irradiation they are high spin states. All right, so under irradiation we change to the high spin. That's why the magnetism changes. But this is not the true, because now with that diagram analysis we have a clue, a hint that it must be low spin F. And now with what we should conclude out of that analysis is that this kind of structure is what we have in as prepared G. Therefore, the right answers are B, D, F. No, wait. Yeah, you must be very cautious. So what I'm doing here wrong that... like this. So under radiation transition from 2 plus to 3. And here is iron 2. So that should be C. Then the correct answers are B, C, and F. Okay. And let's see whether we have some other questions. Yes, we do. And that is also quite simple because you need to put more sodium into the structures. The formula would be sodium 2 cobalt, ferrum CN6. But let's check what the question is about. In the search for an ideal electrode material, these two are applied and mixed together to precipitate under control conditions. And we need to write the formula for the vacant free. And it is indeed vacant free, because if we go to that formula, you remember I've made a mistake here putting 2, and that's because I've miscalculated. For some reason I've put 8, but this is because for some reason I thought that we have occupied all the sites, and there are 8 cubic holes. In this particular structure, as you can see, it's only 1/2 of all the sites are occupied. You can clearly see this. Potassium 1, potassium 2, potassium 3, potassium 4. If you occupy all of them, then in the formula it will be 2. And that is why in one of the latest questions we just write the formula like this with 2 sodiums. So we occupy all cubic holes. And the last question is about writing some equations, which is pretty straightforward. Sometimes the questions are so simple as if it is 8th grade chemistry Olympiad in Estonia. We basically have some electrode which is just pure sodium, and then sodium travels from one electrode side to another electrode side. And when we would like to discharge the battery, then discharge meaning we just use the battery, and you can see that that is probably the usual flow of reaction when highly reactive sodium travels through the whole electrolyte into that structure, and then it fills all the pores and changes oxidation state of iron and cobalt. And that is discharge